Hello to all. I'm Abolfazl from University Charles III of Madrid, and I'm going to present our work within the RefMap project, which is related to flight planning, not only considering conventional kerosene fuel, but also sustainable aviation one. And yeah, thank you. So today I'm going to present the most immediate measures to mitigate the aviation-induced climate impact. I think it's okay. Okay? Is that fine?
Yes.
Okay. So I'm going to skip the motivation for climate change as already presented today by Fatima, and but I'm going to emphasize on the non-CO2 part. So we know that the contribution of aviation to climate change is not only through the CO2 emission, but also through non-CO2 effects. The most important one, or the visible one, is contrails, which are line-shaped clouds that form behind the aircraft. During nighttime, they trap outgoing long-wave radiation from Earth, but during daytime, they can also reflect incoming solar radiation, so contributing to cooling effects. And the effect from contrail is almost 50% of the total contribution. So it's important, but also we need to take into account the uncertainty about its estimation, as can be seen here in this plot. Okay, so we know that aviation is growing very fast, so we need to address its climate change contribution. So the most immediate measures are sustainable aviation fuels and climate-friendly operation, as been highlighted here. So there are different measures, such as technological one, moving toward hydrogen-powered aircraft, but they are not immediate solution, and they consider as medium or even long-term measures. So let's explain how climate-optimized flight planning or operation can reduce the climate impact. Basically, the climate impact of non-CO2 emissions, such as contrails, are highly dependent on the time and location of emissions. So there is a possibility of identifying areas like this, we call it climate-sensitive areas or climate hotspot, and incorporate this information into the flight planning and try to avoid them in order to mitigate their effects. For example, contrails, they require specific atmospheric conditions in order to form. So by flying, for example, a bit lower, we can avoid meeting these conditions and not forming contrails. So flight planning is important for non-CO2 effects. Of course, there is a trade-off with CO2, as also asked in the morning, but we need to consider the trade-off. And regarding sustainable aviation fuel, using SAF, we can reduce the will-to-wake emission of CO2 equivalent by up to 94%, so it's important. But also in operations in general, we are reducing fuel flow by maximum 2-3% because of higher hydrogen content of the fuel. And also, in terms of non-CO2 climate effects, especially contrails, we can mitigate it. How? In order to form contrails, basically, engine emits water vapor and soot. Here we can see two cases. So for kerosene, we are emitting higher soot compared to SAF because of higher aromatic content of the fuel. And then this water vapor from engine condenses on soot particles and forming ice crystals. So for the sustainable aviation fuel, we emit lower soot. So the available water vapor will condense onto fewer soot particles. It means that it gets larger, but at the same time, we are increasing the sedimentation rate. So they fall out faster. So the lifetime decreases and the total climate impact also is reduced. So this is the way that SAF can help mitigating the climate impact of contrails. So these two measures are considered as a short-term measure, relatively shorter than others. Flight planning is something compatible with today because it's related to operation, and sustainable aviation fuel. We have it currently in operation. For example, as presented in the previous panel, the target for 2025 is 2%, and we aim to increase it to 10% by 2030, if I'm not mistaken. So they are relatively immediate measure to mitigate climate. So let's see an example. Here we are presenting a flight from London to Helsinki on a specific day. And it's not important here, but we consider uncertainty due to meteorological condition. It plays an important role in general in estimating the climate impact of aviation because the high sensitivity of non-CO2 climate effects to meteorological condition. And we use a flight planning tool. Roost is a state-of-the-art tool that we have developed. And there is a link to GitHub. And also this is the study that you can find if you are interested about the flight planning tool. Basically, let's see the results. Here we have two routing options. One of them is the cost optimal or business as usual, which is the red one. And we have climate optimal routing option, which considers climate impact in general. So the solid line shows the performance for the conventional kerosene, and the dashed line shows the assessment when considering or using SAF for this flight. If you look at the flight level profile, we are for climate optimal routing option, which is the blue one, we are flying a bit lower. And if you look at NVPM or soot emission here, we see that the dashed line shows that we are emitting lower soot, and this is what we expected in general. Because of burning SAF, it has lower aromatic content. And if you look at the number of ice crystals that form, again, we see that for SAF, the dashed line is lower, so we are forming fewer ice crystals. But the size, if you look at the size, you see it's larger, as mentioned, so it's in line. And in terms of lifetime, if you look at the dashed line, it's lower. So, and in terms of effect, which is the most important one, EF is energy forcing, a metric to estimate the climate impact of contrails. So the interesting results are here. For the routing option, cost optimal or business as usual, we are forming warming contrails, basically because this is the accumulated value. Because it's positive, it's warming. If we use SAF for this routing option, we are a bit lower. And this is because of reducing soot and also lifetime and the impact. So it's beneficial for this routing option. But what happens when we use it for a routing option that avoids forming warming contrails and create cooling contrails? So this blue one, by flying a bit lower for this case, we are avoiding forming warming contrails and we are creating cooling contrails. But for this flight, if you use SAF, we are reducing cooling potential, and this is expected. So we know that we have limited SAF, so we need to smartly use this SAF. Only use it for flights that forming strongly warming contrails, and do not use it for cooling, because here we are reducing potential. And maybe it's interesting to see how these results are obtained. Basically, here we have two routing options. So the yellow one should be, okay, so yeah, there is a mistake here in the plot. So basically the yellow one is the blue one here, and the blue is the red one. This is, so this is the flight level that is chosen by cost optimal routing option, and the blue one is the cost optimal. So we are creating warming contrails. But for the climate optimal one, which we fly lower, we are flying at this flight level. And we are deviating from shortest path to maximize cooling contrail formation. So this is the way that we obtain these results. Okay. So we just 3 minutes, okay. We just speak about the potential of these two measures, but they are associated with challenges. Here, the first challenge is for the climate optimized flight planning is due to the degradation of operational manageability, as discussed in the morning by Fatima, and also in terms of sustainable aviation fuel. there is an issue with the availability. So we don't have it, currently I think about 1%. So we need to smartly use these two measures to maximize the benefit, but considering the current limitation and also operational manageability. So the concept that we introduced in the RefMap project is basically to smartly using these two measures, or the targeted use of these two measures. So we are given a traffic for each flight. We optimize considering different routing options. By routing options, I mean different trade-off solutions. So one of them is the cost optimal, and the other one is climate optimal, or different intermediate solutions. And use different blending ratio of SAF for these flights. And in the end, we have a decision making that we use only one option for flight, one routing option and one blending ratio, such that some high-level criteria are met. For example, we impose SAF availability, the extra cost, maximum number of rerouted flights, so all these conditions. And so considering the fact that I don't have much time, I'm going to present some large-scale results. So that one was specifically for one flight, but here we have a yearly analysis, so performing optimization for a year of data. And we see that here we have only climate optimized flight planning. And for the cost optimal, we don't have any mitigation in general. But for the blue one, which is climate optimal routes, we can have up to 78% mitigation. If we allow for higher cost, for example, going from 0.01% extra cost, why extra cost is important? Because we are deviating flights. So we need to impose constraints to make them attractive for stakeholders. So if we go for example, 0.01 to 0.5, we can gain even double. So this is the way. And how it is obtained. During winter, we are avoiding forming warming contrails because it's not possible to have cooling contrails during winter. But during spring, because of increased solar radiation, it's possible to have cooling contrail formation, so we deviate flights to form cooling contrails. And let's see. Okay, I'm going to just go to the last slide, which we have all the results together because of the time. So here we have several routing options. The first one is the cost optimal routes, and we use 2% SAF, uniform distribution. So all the flights with 2% SAF, 2% blending ratio, we can say, and the mitigation potential is only 1.38, so it's nothing. But why 2% is because of the target for this year. If we go for climate optimal route, a smart distribution. So we may go for a flight and use 100% SAF for that one, but a flight we don't use any SAF. And for this case, we can have up to 48% mitigation. How? We only use it for flights that form strongly warming contrails. If we go for climate optimal routes with kerosene, we see 78, we saw it previously. But if for this climate optimal routing option, we use as 2% SAF uniform distribution, again, we don't see that much mitigation. But if for climate optimal routing option, we use a smart distribution of 2% SAF, look at the mitigation. So it's 109. Basically, when using SAF, 2% SAF that we will be having available by end of this year, hopefully, we can have 30 to 40% more reduction for the cost optimal and climate optimal option. The last slide, which I guess is the most important one, and the message is that here we are allocating more SAF to see how the benefit changes, and we see that by 5% smart use of SAF, we are done with the maximum potential for contrail climate impact reduction. It's important to note that it's contrail. We know that for CO2 we can linearly gain in general. But this is for contrail, which is the most important non-CO2 forcing agent. And by 5%, which is the target, I guess, for 2027. I think, I'm not sure if it is exactly the target, but we can get the maximum reduction. So yeah, thank you very much. That's all.
Thank you, Abolfazl. One question. Please go ahead.
Hi. In one of the first slides, you said that you wrote that the two means we have to mitigate the impact of flying is sustainable aviation fuels and climate-friendly operations.
Yeah.
And that the amount of flying that we're doing is increasing.
Yeah.
I have a two-part question.
Okay.
Come on.
If it is increasing, is the optimization taken up by the additional traffic? Because I've recently read some research that says that all the savings from sustainable aviation fuel are more than erased because there's more flying. And also, is your work linked in any way to reducing demand?
Okay, so for the demand, okay, so basically the change in the transportation mode is necessary. So what we are saying basically is with the current operation. So the short-term measure, of course, if we go for 2035, we will have hydrogen-powered aircraft in operations and hybrid electric aircraft, so the demand can shift. Maybe they banned some flights, short-haul ones. So yeah, but this one, I emphasize that it's the short term. So when we are waiting for those measures to come into play, we can rely on these measures, basically. But the demand, well, it's evolving. It's a bit, I think, not quite sure, but I think this measure can still be beneficial when we compare. So basically, we compare with business as usual operations. So in that case, if we have a business as usual operation, then we reroute flights or we allocate staff to some of them, then we can see the mitigation, basically.